Hello everyone and welcome to chapter 0 video number 2 in the 3-phase induction motor course. In this video we are going to cover AC source and AC circuits revision. So these are the tools we are going to use in the 3-phase induction motor. But if you want more details about AC source and AC circuits, this is not the video you are searching for. There will be a different video explaining in details AC source and AC circuits. Let's start by a sinusoidal waveform. Assume we have a sinusoidal function like f of t equal f maximum sine omega t plus or minus theta. So what's f of t? F of t can represent voltage, current, or even flux. So we need to identify some important values here, like this one. So what this one? Positive f maximum, positive peak value or the amplitude of the sine wave. And we have a negative peak as well. If we put this waveform in the scope, we can measure what we call it peak to peak equals 2f maximum. For example, if we have a voltage equal 10 volt, so peak to peak equals 2 multiplied by 10 equals 20 volts. T, capital T, represents the periodic time, so this waveform is going to repeat itself every capital T. But if we put the x-axis in function of the angular frequency omega, so this waveform is going to repeat itself every 2 pi. Omega is measured in radian per second or 1/2, and omega equals 2 by f, very important equation, the relation between the angular frequency and the frequency. So what's the frequency? We can say that the frequency is the supply frequency, if you like to say that one. And the frequency is measured by cycle per second or hertz, and the relation between the frequency and the periodic time 1/t. So what about theta? So this waveform is plotted starting from the 0 point, so theta here equals 0. Theta represents the phase shift. But if the waveform is delayed by a certain angle, right, or the waveform starts by a certain angle before the 0 point, so we are going to substitute by theta. So if theta 1 here, so f maximum sine omega t minus theta. If we're going to substitute by theta 2, f maximum sine omega t plus theta 2. There's another component or another value which is very important value in the sine wave. We call it the root mean square or the effective value. So how to calculate the root mean square or the effective value? Root 1 over the periodic time t, integral from t naught to t naught plus t, which is 1 period, the functional square of t dt. So if we substitute by our sine wave here, we are going to calculate this function, 1/t integral f maximum square sine square omega t plus or minus theta. We are going to find that the RMS value equals the peak over root 2. Please note, this value is only for the sine wave. If we're going to have something like square wave, the RMS is not peak over 2. The RMS in this case equals the peak value. So you need to resubstitute here again by a square wave. Triangular wave, you are going to substitute in this equation to find the RMS value. So for the sine wave, the RMS, for example, IRMS equal I peak over root 2. So here we identified the important values for the sine wave, the peak, the RMS, what is the angular frequency, what is the frequency, what is the periodic time, and what is the phase shift. Let us take a quick refreshment about AC circuit elements. In AC circuits, we have resistance measured in ohm, inductance measured in Henry, and capacitance measured in farad. So the voltage and current relationship, that V of t equals I of t multiplied by the resistance R for the resistive elements, and V of t equals L the I of t by dt for the inductive elements, and V of t equals 1/c integral I of t dt for the capacitive elements. If the supply is sinusoidal, so we can write this equation as VRMS equal IRMS multiplied by the resistance R, and VRMS equal IRMS XL for the inductive element. If we substitute by a sinusoidal function here, and we are applying this equation, we end up by this term XL, where XL equals J omega L. Omega equals 2 by F, as you know from the previous slide. And XL has an angle 90 degree, and that one is measured in ohm. Right. Regarding the capacitance, so VRMS equal RMS XC, where XC equals 1 over J omega C, and XC has an angle minus 90 degree. So looking for the waveforms, in case of the resistive load, the voltage and current are in phase. So if the voltage V has an angle 0, the current has an angle 0. If the voltage has an angle 30 degree, the current has an angle 30 degree. So we can put that one in a phasor form, as we can see here. V and I are in phase. So that one could be RMS value or could be peak value. In terms of inductive load, we are going to find that the current lags the voltage V by 90 degree. We put that one in phasor form, so I lags V by 90 degree. For the capacitance, the current leads the voltage by 90 degree, and in this case, I leads the voltage by 90 degree. In this slide, I explained the elements as pure elements, pure R, pure L, and pure C. What will be the case if we have a combination between R and L or R and C? In this circuit, we have a sinusoidal supply feeding RL load, so definitely there will be a current in this network. And because the supply is sinusoidal, so XL equals J omega L, as we know before. So here we have what we call impedance, Z equals R plus JXL, where impedance consists of a real part and imaginary part. Real part is the resistance, imaginary part is the reactance. So we wrote the impedance here in the rectangular form. We can convert the rectangular form to polar form, where the amplitude of the impedance will be root R square plus XL square. And the angle of the impedance, which represents the power factor of the circuit, equal tan inverse XL over R. Please don't forget the brackets when you are going to substitute in your calculator. So in this case, we can write the voltage in phasor form, where V angle theta V equal I angle theta I, Z angle phi, where phi equal theta V minus theta I. So if we look for the phasor diagram here, if we have a pure resistive element, so the current and voltage will be in phase. If we have pure inductive element, the current is lagging the voltage by 90 degree. So definitely if we have RL, the current is lagging the voltage by angle phi. Look for the waveforms here, so the current is lagging the voltage by this angle phi. What are the applications for RL load? So something like fluorescent lamps, air conditions, any dynamic load like motors, compressors, fans, pumps. Similar to the inductive loads or RL loads, we can have RC loads fed from a sinusoidal supply V of t, as you can see in the figure. In this case, XC equals minus J1 over omega C. We can write the impedance Z equal real part, which is the resistance, minus JXC, which is the imaginary part. And in the rectangular form, we can write Z equal R minus JXC. We can convert the rectangular form to polar form, where the magnitude of the impedance Z equal root R square plus XC square. And the angle phi of the impedance equal tan inverse XC over R. Please, again, don't forget the brackets. So in Ohm's law, V equals IZ. Let's look for the phasor diagram here. If we have a pure resistance, so the current and voltage will be in phase. If we have a pure capacitance, the current leads the voltage by 90 degree. So definitely if we have a combination between R and C, the current will lead the voltage by an angle phi. So what are the applications for RC loads? Something like switch mode power supplies, electronic ballast, or motor starting capacitors. For impedance calculation, if we have a group of impedances that are connected in series, we are going to find the equivalent impedance by adding them together. But we need to take care here. If Z1 equals R1 plus JX1, and Z2 equals R2 plus JX2, and Z3 equals R3 plus JX3, so the equivalent impedance will be R1 plus R2 plus R3, adding all the real parts together, and this will be the real part of the equivalent impedance. And then adding x1 plus x2 plus x3, and this will be the imaginary part of the equivalent impedance. If we have two impedances are connected in parallel, So we can use this equation, Z equivalent equals Z1, Z2 over Z1 plus Z2. But to perform this one, we need to add Z1 and Z2 in the rectangular form, and then we can convert that one to the polar form. So we add those together in the rectangular form, and then we convert that one to the polar form. And we are going to multiply Z1 and Z2 in polar form, and then we are going to make this division. So we know that if we're going to multiply two complex numbers in polar form, we can multiply the magnitude and add the angles together. But if we're going to make a division, we're going to divide the magnitude by the magnitude and subtract the angles. Let us see how to calculate the power in AC circuits. But you write here single phase power. We need three-phase power. We're going to take that one as a step to calculate the three-phase power. We have three types of power: active, reactive, and apparent. So the active power is the power P measured in watt equals Vrms Irms cosine phi. Phi is the angle between the voltage and the current, or the impedance angle. And cosine phi represents the power factor of our circuit. If we have RL load, so we have lagging power factor. If we have RC load, we have leading power factor. If we have a resistive load, so cosine phi equal 1, and that one is unity power factor. Also, we can calculate the power P equals I square R, RMS value, I square RMS R. So for the reactive power, it's measured in VAR, volt ampere reactive, and Q is a symbol of the reactive power, equals Vrms Irms sine phi. Phi is the angle between the voltage and current, and you can calculate it from the power factor cosine phi, or cosine inverse phi, give you the angle phi, then you can calculate sine phi. So Q equals Vrms Irms sine phi. Also, you can calculate Q as I square RMS X. X could be reactive, could be capacitive, so it depends. So Q has a positive value if it's inductive, so that one positive if it's inductive, or negative if it's capacitive. Right. So we can have P and Q, and the total between P and Q using Pythagoras is S, which is the apparent power, measured in volt ampere, and this is the angle phi. So S equal V RMS Irms, has a magnitude and angle. And also you can calculate S, which is the apparent power, I square RMS multiplied by the magnitude of the impedance set. But according to Pythagoras here, S equal root P square plus Q square. You look for the triangle here, Q equal S sine phi and P equal S cosine phi. That one is going to help us to calculate the three-phase power. Let us take an example. For the network shown in the figure, find the voltage, current, active, reactive, and apparent power for each branch. So my advice to you is to stop the video now and try to solve the problem. And once you finish, you can return and resume your video to see the solution. Let me remind you that stop and play buttons are not active buttons. They are just simple. So let's look for our network now. We have a voltage source, sinusoidal supply, with RMS value 148 volt, angle 41 degrees. The supply frequency is 50 Hz. And we have three branches. RL, I'm going to call that one Z1. RC, I'm going to call that one Z2. And pure resistance, I'm going to call that one Z3. So now we can convert this network to Z1, Z2, Z3. It's easy to configure the solution now because Z2 and Z3 are in parallel. Once you get the parallel combination between Z2 and Z3, you can add it to Z1. So you find Z equivalent, and then you are going to find the total current from the source, I1, and then you are going to distribute the current here, I2 and I3. If you get the current in each branch, you can find the power. So let's write Z1, but we have a problem here. That one is 6.4 millihenry. It's not in ohm. Don't forget that XL equals omega L and XC equals 1 over omega C. So Z1 will be 3.5 plus J2. Z2 will be 20 minus J15, and Z3 equals 24. I can write here plus J0. There is no imaginary part. So to make the parallel combination between Z2 and Z3, we need conversion between rectangular to polar and polar to rectangular. So you can do that one using your calculator, either using complex mode, or there is a button is called POL, polar. So you are going to convert. For example, we are going to convert Z2. POL 20, comma, minus 15. That one give you magnitude 25 and angle minus 36.8. So at that time, you can write Z2 equals 25 angle minus 36.86 degrees. So now how to find Z23, which is the parallel between Z2 and Z3. So Z23 equals Z2, Z3 over Z2 plus Z3. So to have a multiplication here, so you are going to multiply polar forms. You are going to add here, so that one should be in rectangular form, or as I mentioned, you can use complex mode. So to do that one, we have Z2 plus Z3. So that one will be in rectangular form. I converted to polar as well. And the equivalent impedance Z23 will be 12.91 angle minus 18 degrees also. So we can convert that one to rectangular form, either using complex mode or use the button rec. So you are going to write here REC 12.91, comma, minus 18.04, and that one give you the real and imaginary parts for your impedance. So Z23 end up by 12.27 minus G4. So we got the value for this part. Now, we are going to add it to Z1 to find the equivalent impedance. So Z equivalent equals Z1 plus Z23. We can put it in polar form or rectangular form. It's time now to find the supply current. We have Z equivalent, so V supply over Z equivalent give you I1. So supply current equal 148 angle 41 degrees over the Z equivalent in the polar form give you the current 9.3 and angle 48.3 degrees positive. So this means that the current is leading the voltage by angle 7.3 degrees. And our network, the overall network, is capacitive circuit, it's not inductive circuit. So how to find I2 and I3? There are different scenarios. Either you find the voltage between these 2 points, I'm going to call them AB points, so that one is voltage VAB. And using Kirchhoff voltage law, where V supply minus I1 Z1, you can get VAB. And once you have VAB, you divide VAB over Z2, you get I2, and you can get I3, where VAB over Z3 in this case. Or use current divider rule, so you have the supply current I1. If you like to calculate I2, so I1 multiplied by Z3 over Z2 plus Z3, as I calculated here. So the current I2 equals 4.8 angle positive 67.12 degrees ampere. And to calculate I3, either use Kirchhoff current law where I1 minus I2, or using current divider rule as well, where I1 multiplied by Z2 over Z2 plus Z3. So in this case, you are going to find that the current here, I3, 5 angle 30 degrees. Once you have the current everywhere, you can calculate the power. So let's look for the source power, input power. Active power, V supply, I supply, cosine phi. So that one will be 148 multiplied by 9.3 cosine theta V minus theta I, which is the impedance angle, the equivalent impedance angle 7.3 degrees. So that one will be something like 1.36 kilowatts. You can calculate Q. Instead of cosine, you're going to put sine phi, but don't forget that we have now capacitive circuit, so Q is negative 175.4 var. S, you can calculate it as V supply, I supply, or you can use the equation root P square plus Q square. So now we need to check that we have the correct input power. So we can calculate that one using sigma I square R for the P. So for example, that we have Z1 has 3.5 ohm. So that one equals the current, which is 9.3 square multiplied by 3.5 plus the current in Z2 is 4.8. So that one is 4.8 square multiplied by the resistance of this impedance, which is 20 ohm, plus 5 square multiplied by 24 ohms. If you add up all of these values, you are going to find something like 1363 watt, which is very close to the value we calculated here. So that one is accepted tolerance because we have here cosine and sine. You can do the same for Q. Q equal sigma I square X. But please don't forget that for Z1, X is positive. So that one will be 9.3 square multiplied by positive value. For Z2 will be negative value because that one is capacitive. For Z3, there is no reactive power. So we are going to check that one as well. And if you like to calculate S for each impedance, you can do that one like I square magnitude of Z, or you are going to calculate root P square plus Q square. So let us look for the circuit as if we build the circuit in the lab. So we have a supply voltage. We are writing the voltage in time domain, 148 root 2, the peak value, sine omega t, plus 41 degrees. RMS value will be 148 angle 41 degrees. So that one is theta V. And the current will be 9.3 ampere. That one is the supply current, 9.3 ampere, angle 48.3. So that one is theta I. The difference between theta V and theta I give you the power factor of this circuit. You notice here that the current is 9.3 ampere if we measure using a meter. And the voltage across this branch will be 37.5 volts. And the voltage across the parallel branch is 120 volts, as you can see here. The current through the resistance is 5 ampere, and the current through this branch is 4.8 ampere. If you like to measure the power or calculate the power, so I square R in this resistance give you 600 watt, and I square in this resistance give you something like 460.8 watt, and here something like 303 watts. Add them together, they are close to 1365 watts. Regarding the VAR, so the capacitance is going to take negative VAR as we can see here, and the inductor is going to take a positive VAR as we can see here. Add them together, you are going to check that the input VAR from the source is something like minus 175 VAR. You can do the same for the S. But if you notice here, ammeters and voltmeters in the lab are measuring RMS value. Can we measure the value or the magnitude and angle? So let's look. I built for you a Simulink model here to show you that how we are going to calculate the magnitude and angle. But how I'm going to build a circuit like this one using MATLAB Simulink? Let me tell you that there will be separate sessions or separate videos for learning how to build a circuit like that one using MATLAB Simulink. And our main target is to build a three-phase induction motor in this course. But here, I added the simulation to confirm the analytical results we did in the previous slide. So the supply voltage is 148 volt, angle 41 degrees. Supply current is 9.3 ampere, angle 48.2 almost. And the current in this resistance will be 5 ampere, angle 30 degrees. And the current here is 4.8 and angle 67 degrees. So now you can add different blocks to calculate the power in this resistance, power P, Q, and even the power from the source. Let's look for the waveform between the voltage and current. So supply voltage is the blue waveform, and supply current is the red waveform. So it's clear here that the current is leading the voltage by a certain angle. So theta V minus theta I, so that one will be something like 7.3 degrees. Now you can calculate the power factor for this circuit. Cosine phi cosine 7.3 degrees give you the power factor for this network. So now after we finish this example, now you learn how to make a quick analysis using AC circuit, how to calculate single phase power, P, Q, and S, and that one will be a good start for the three-phase induction motor when we are going to solve the three-phase induction motor per phase. But still we need to learn about the three-phase. Let us take a quick revision about three-phase circuits. We have in three-phase circuits two configurations, either star connection or delta connection, as you can see here. We're going to look for one by one how to find the relation between phase voltage and line voltage, or phase current and line current. So here we're going to cover a quick revision about star and delta loads. But if you like to cover the three-phase circuits or polyphase circuit, this is not enough. You need to visit the three-phase course. There will be a course dedicated for three-phase or polyphase circuits. Let's look for the three-phase star connection. We have phase A, we have phase B, we have phase C, and we have a neutral point. So we have the voltage for phase A is connected across this impedance between A and N. So we have phase voltage VAN. And if the voltage is going to be measured between A and B, so that one we call it line voltage or phase-to-phase voltage. Looking for the equation that VAN equal V angle delta, it's not necessary to be zero any angle, but phases B and C should be shifted 120 degrees from this one, right? What about the line voltage? The line voltage equal √3 the phase voltage and leading that one by 30 degrees. And definitely phases B, C, and CA, the line values between BC and CA are shifted 120 degrees from this one. Look for the current here. The current in the line is exactly the same in the phase. So we're going to have here phase current equal line current in the star connection with 13 angle. It depends on the impedance nature. R, RL, RC. So there will be a power factor angle, which is cosine the angle theta V minus theta I. So let's summarize that one. The line voltage leads the phase voltage by 30 degrees. The line voltage equal √3 the phase voltage. And the line current equal the phase current. And the angle between the phase voltage and phase current is the load impedance angle, which reflects the power factor of the load. And for balanced load, the circuit can be solved per phase, which is good when we are going to analyze the three-phase induction motor. So we can solve the circuit per phase and then multiply by 3. What is the difference between delta connection and star connection? In delta connection, we have the load is connected, as we can see here. There is no neutral point, and the voltage between phase A here and phase B represents phase voltage or line voltage at the same time. But the current through the load, through the impedance here, we have I subscript small a and I subscript capital A. So there is a phase current and line current. They are totally different, right? So what are the equations? So the voltage VEP equal V angle delta. As we mentioned, could be 0, could be any value. And VBC and VCA are shifted from that one by 120 degrees. Right. The phase current, which is I, small a, is I angle theta. And phases B and C are shifted 120 degrees from this one. But the line current here is √3 this value. So as you can see here, line current equal √3 phase current, but lagging this one by 30 degrees. So let us summarize like the star connection. So the line current in delta connection lags the phase current by 30 degrees. The line current equal √3 the phase current. And line voltage equal the phase voltage. And like the star connection, the angle between phase voltage and phase current is the load impedance angle. And that one represents the power factor of the load. And for balanced load, the circuit can be solved per phase. And that one will going to help us in analyzing the three-phase induction motor later on. If the motor is star connection or delta connection, we can solve the circuit per phase and then multiply by 3 if we need to calculate any power. Now it's time to see how to calculate the three-phase power. So the three-phase power is similar to the single phase. We have active, reactive, and apparent. So for active power measured in watt, P equal 3 V RMS cosine phi, or 3 V phase I phase cosine phi. We can write this equation by another way. P equal √3 V line I line cosine phi. Please note, cosine phi here is exactly the same like cosine phi here. And phi is the angle between V phase and I phase. So let me repeat again. If you are going to use this equation, 3 V phase I phase cosine phi, so phi is the angle between V phase and I phase. if you are going to use this equation, phi is the angle between V phase and I phase, not V line and I line. Right. So P you can calculate it as 3I square R, or using the power triangle PQS. So that one is PQS. That one is the angle phi. So P equal S cosine phi. Regarding the reactive power and volt ampere reactive, you can use the equation 3V phase I phase sine phi, and phi is the angle between V phase and I phase. Also Q we can calculate it as root 3 V line I line sine phi, and phi is the angle between V phase and I phase. Also Q can be calculated as 3I square X. For inductive load, that one will be positive. For capacitive load, that one will be negative. Or using the power triangle will be Q equal S sine phi. So regarding the apparent power is measured in volt ampere. So that one is 3V phase I phase. Or we can write that one S equal root 3 V line I line. And also you can calculate that one using the amplitude of the impedance, or S equal root P square plus Q square. Let us summarize this video. In this video, we covered sinusoidal waveform, AC circuit elements, R, L and C, RL loads, RC loads, and how to calculate the impedance in series and parallel. And then we looked for single phase power, how to calculate P, Q, and S, and we solved a detailed example regarding single phase circuit and how to make impedance calculation, how to calculate the current in each branch, how to calculate the power factor. And then we revised the three-phase loads, star and delta connected loads, and then how to calculate the three-phase power. So, what will I watch in video number 3? On the next video, we are going to cover magnetic circuits. We're still in chapter 0, which is a revision chapter, so we are going to cover magnetic circuits. See you in the next video.